Okay, so now what is the trick over here? You know that to do an approximation, generally what we do is what? Assuming that t minus t sub n, okay, which this will be, okay, so if assuming that t over t sub n is small, basically that means that t minus t sub n is small, then in that case what happened? We're gonna have that t minus t sub n square would be even smaller, and we can say that t minus t sub n to the k would be even smaller. Okay, so we can neglect the higher terms because this will be very small compared to the t minus t sub n, and in that case the Taylor expansion will reduce to what? This term and this term only, and the Taylor's approximation reduces to what? So we're gonna have y of t. Now I remove the equal sign because this, if we go to infinity, will be exact, but this becomes just now an approximation. Will be y of t of n plus dy dt at Tn t minus t sub n, plus this will mean that we have an approximation of the order of t minus t sub n square. This will be the error that we are introducing. Okay, so this basically will be the second order or second term Taylor approximation. Okay, so 1, 2, so will be second, oops, we cannot say it, second term Taylor's approximation. Alright, so let us go to the next page. And that will be page 128. Okay, so if we know the Taylor expansion for y of t here, all right, what is our differential equation? Is dy dt. So let's see what would be the second term approximation for dy dt. Okay, and I can write here, and the approximation for dy dt at the end is what? So then we'll have that dy dt at the end will be equal to what? So we see that the term is over here. Okay, dy dt is over here, so we just need to solve for this one. So what would that be? Would be y of t minus y of t of n divided by t minus t sub n, plus now the order, but instead of being to the square, would just be to the order 1. So this would become what? dy dt dn is not equal, approximately equal to y of t minus y of tn divided by t minus tn plus an order, but this time this will just be to the order t minus t sub n. Will not be to the square anymore, but just to the order 1. Alright? So here now, if we say let t over here can be any time step, so this will be the forward Taylor approximation. Let's say will be t n plus 1. So we look in the future. If you want to do the backward, you can just say t equal t minus 1, and then in that case, what will you have? This t would be t n plus 1 minus t of n, and let's just say that this, we're going to call this delta t, where delta t is our time step. Okay, so this is the forward substitution. If you want to do the backward substitution or Taylor expansion, you would just put t to over t minus 1. Okay? So in that case, what do we have? So that the Taylor approximation for the first derivative will be ty tn at tn approximately equal to y. I change a bit the notation instead of putting on the t, y of n divided by delta t plus epsilon of the 0 order delta t. So this will be what? First order will be because of the order here of delta t, not delta t squared, first order. Finite difference approximation of what? Of the first derivative. Okay, so over here I just want you to notice something, is that this is a mathematical expression, and you see that comes from the Taylor expansion, okay, which you might be familiar. But here I want you to notice one thing. Notice that dy dt, I'm going to remove the t sub n equal to y n plus 1 minus y sub n divided by delta t. What is that really? Okay? That, if you remember, let's say if we do here a little figure, where this would be t, this would be y, and let's say we have a general function here, this would be a general curve. So how can you approximate this curve? Okay, so let's say we look here at a point A. We know this could be approximated by the tangent. Okay, so it would be what? This would be the dy dt. So obviously the tangent is going to be the more accurate the closer the 2 points. Let's say you have a point over here, you have 1 point over here and 1 point over here, the tangent is just going to cut, it's not going to be accurate. But if you start moving closer to the point here, and if you go through, then the tangent will be more accurate. And if you put the 2 points extremely close to each other, then the tangent would be accurate. So basically this is called a finite difference, but if you want to look at it from on a figure, this is really the definition of the tangent at a point. Okay? Alright, so just wanted to notice that this term is as well the definition of the slope, okay, slash derivative slash tangent at a point. Okay, so basically this is your y of t. So you can now predict the location of every point A on y of t if you look at the tangent at every single point. So you can see that the solution will be more and more accurate as the distance between the 2 points, or the time step, will be small. Okay, so let's say this time step over here. So the closer the 2 points are through which you can draw the tangent to the point, the more accurate will be the solution to the equation at that point. Alright? Alright, but now remember what we're trying to do is to find the numerical approximation of the ODE. So let us go back. So let us go back to the ODE, to our initial ODE, which is what? dy dt equal to f y of t. Okay, and if you want, okay, we can leave it this way. So now this, using this definition here, we can write this as what? Use the definition over here, will be at yn plus 1 minus y of n divided by time step delta t will be equal to f at the time n y of n t of n. So this will be v1 at t equal to tn. Okay. So we have this. Remember, this is the exact, so we move here to the approximate, so it's not that important, but let's put it over here, and this will mean what? That yn plus 1 minus y of n more or less equal to f of y of n t of n times delta t. So now from this expression, $128 27, 28 was 29, that was correct, so 129. Okay, so now that we have this from the previous expression, we can find that at the next step yn plus 1 will be equal to yn plus f of y sub n t of n times delta t. Okay, so here we have our first approximation on how to solve the first order ODE. And this actually is called the Euler approximation. okay, which will give what we're going to be calling the Euler's method later on. Okay, I want you to notice that Euler's, I think, was late 19th century, late 18th century or early 19th century. So basically no computers, no calculators. So people in those days were still trying to estimate the behavior of a first order differential equation by performing this approximation by hand. Okay, so that was a very tedious work. Okay, all right. So again, this is a first order approximation method for first order ODE. All right, so we can say the above approximation method is delta t order accurate. So that means first term or first order accurate. So, and this means that if delta t is half, then the error is half as well. Okay, this is correct, but it's not 100% correct. This would be 100% correct if the function was 100% linear. But as we mentioned, this sometimes is used to solve, or in most cases, to solve nonlinear differential equations. So in that case, it's not like the solution is going to be just exactly half better, but of the order of half, okay? Depending on how much nonlinear is this. So in other words, if I take this curve over here, if this was a straight line, let's say the solution y of t was a straight line, yes, if you take y of t to be half, maybe I can do here a little figure. So that means that okay, if our function is of this shape here, then yes, if you take half the time step, you can estimate the solution to be half better. Okay, but what happens, let's say, if this curve here is of the of this form over here? So you see that this time step over here, let's say, I mean, this is almost linear, but let's say you take it between, and it does this. So let's say you have these 2 points here. This is not because you take half. Actually, if you take half, you're going to have a much worse solution. All right? So you need to be careful over here. There's a change in the direction. That doesn't mean that always you're going to get a half a solution better. Sometimes you may even get worse. Okay? That depends on how abruptly this function is changing directions. Alright, so this is basically the theory. So in general, the discretization solution. So discretize means basically breaking the solution into multiple discrete intervals. Y sub n might be approximated as what? As what we just mentioned, y n plus 1 equal y of n plus f y of n t n times delta t. Okay? And this is exactly as we have for the Euler methods. But you can do other approximation, and in that case, this is kind of, you can see it written in different books as y of n will be equal to y of n plus the summation of, let's say, b sub I, k sub I, alright, and times delta t. And you will see, so this will be, as is known as the Euler method of first order approximation, but you have higher orders approximation that will be basically, instead of having this fy of n, you will have different expression for y f of n will be equal to this over here. Alright, and what is peculiar over here is that you will see that this term over here really will be the case, or will be sub I. B sub i's will always be equal to 1. Okay, I'm going to do that right away. So first method we have is what? Is the Euler's method. That gives us what? This one is accurate to the order delta t. Alright, and here we're going to have an approximation where k1, so will be that k over here, is equal to f y of n tn delta t. So you see this expression will be, and in that case you will have k1 is equal to this, b sub I will be equal to 1, okay, directly. So that you can have over here yn plus 1 is equal to y of n plus k1. Alright, but okay, if you go to the Taylor expansion, and let's see if I can go back to this page. If you go to the Taylor expansion over here, and this time you keep up to the second term, so you keep this term, this term, this term, but neglect all the other terms, following the same procedure and with some other manipulations, it's not that complicated. You will find that oh, actually this is just the midpoint, so the next one is just, instead of going from one point here to a point, you calculate the next point by just first going to the middle point. Alright, and that's what is known as the modify Euler's method, also known as the midpoint method, and this one would be of the order delta t square approximate. Alright, so the equation for this one, you see first you calculate k1 equal f of y of n tn delta t. Now you use the middle point would be f of y of n plus k sub 1 comma t of n plus delta t. Alright, and now you do y of n plus 1 will be equal to what? Y of n plus 1 half k1 plus k2. Okay, now did you see what I told you here, that this will always be equal to 1? So what do you get here? 1 half plus 1 half will be equal to 1. Okay? Alright? And then there is actually, we're going to look at two more methods. So it will be page 130. The other one is the Heun's method. And this one, also will be to the order delta t square accurate. I should have done that in blue, but too late. In this time we have k1, same as before, equal to f y of n tn times delta t. K2 will be equal to f y of n, but this time this will be, instead of plus k1, 2/3 k1, and the time step will be tn plus 2/3 delta t. So what do you think will be yn plus 1? We know will be y sub n plus what? K1, so we put here K1 plus 3K2, and we know this should be equal to 1, so this should be 1 plus 3, 4, 1/4. Alright? And this will be Heun's method. Alright, and the last one, and probably the most widely used numerical method, is the one known as the Runge-Kutta method, and this one is of the order to the 4th. Okay, so in this case we're going to have again k1 equal to f y of n tn delta t. Oops, I think I forgot here to multiply by delta t. See if I forgot on the other one. Yes, I forgot as well on the other one, so be careful here. Forget here to multiply by delta t. I think the rest will be okay. So now we produce K2 at the half step, y sub n plus 1/2 K1, and this you do that at t sub n plus 1/2 delta t. And let me not forget to multiply here by delta t. K3 is equal to f of y sub n plus again 1/2 of this time K2 at tn plus 1/2 delta t times delta t, and K4 will be equal to f of y sub n plus K3, and this will be tn plus delta t times delta t. So at the end, yn plus 1 equal to yn plus what? Leave some space over here. K1 plus 2K2 plus 2K3 plus K4. So how many we have? 1, 3, 5, 6. So then at the front will be 6, so that all these terms, the b sub y, are equal to 1. Alright? And this is the Runge-Kutta. So these two methods probably are the most widely used nowadays in numerical methods. Alright? So let us do an example. Alright, so let's go. So example. And to save some time, I'm just going to take an existing problem we did before. So given the initial value problem, dy dt equals sine 2t minus y tangent t, with the initial condition y of 0 equal to 1, where this is our initial condition. So if you recall, recalling from 126, the exact solution is y of t equal to minus 2 cosine square of t plus 3 cosine of t. So obviously the reason why we want this exact solution is so that we can compare our numerical solution to the exact solution and see how accurate it is. But remember that in real life you're not going to have this luxury to know what is the exact solution. So for you to know that you are getting a good approximation, you need to at least see once what are the kind of difficulties you can have by doing an approximation of the solution of an ODE by numerical methods. Okay? Alright, page 131. Okay, so without going into too many details, I'm just going to go through generally the steps. So, approximate the solution numerically. So basically it means using the Euler's method, the midpoint method, the Heun's method, and the Runge-Kutta method. Okay? Using the Euler's method, the Euler's midpoint, Heun's, and Runge-Kutta method. Okay, one thing here, some people think that Runge-Kutta was actually just one person, but actually Runge was one, I think, German mathematician, physicist, and Kutta was from another country, but basically they both came up at about the same time with the same solution, but these are two different persons, okay? It's not just one person. Alright? Approximate the solution numerically using the Euler's, midpoint, Heun's, and Runge-Kutta method. Okay, method, that's fine. Alright? So basically we know we take the equation, okay. I just want to here note that fy of t equals sine 2t minus y tangent t. Okay? Is singular at t equal what? So when is this equal here to 0? Will be at pi over 2, 3 pi over 2, and so on. Every time you have a pi over 2. Okay, so this would be singular at this point, and it may create numerical breakdowns that will be addressed later. Okay, so now we're going to go into some MATLAB codes. Alright, and for that I'm probably going to have to shut this video and create another video because I cannot record whatever I'm doing on the screen. But basically I give you a quick summary here. You have some MATLAB codes. So the Euler method, the name of the file or the function would be ODE1. Then the modified Euler's method will be the ODE2. Then the Heun's method will be ODE2H. So basically you see the 1 means first order approximation, 2 second order approximation, this is second order approximation, the Heun's method, and at the end the Runge-Kutta method or approximation would be, as you can guess, ODE4. Okay, and actually you will see on the on this lecture, but on the following one you will have another one that would be the Runge-Kutta but with some time step adaptation, and that would be the ODE4H. Okay, so I'm going to conclude the video over here for this, and I'm going to create another video showing you these MATLAB files and how they work. Thank you for your attention.